So we're going to talk about torque and do a couple of example problems. The equation for torque is R times F times sine theta. So R is the distance between the pivot point and the point at which the force is being applied. F is the force, and then theta is the angle between the radius vector and the force vector. The symbol for torque is a tau. It's a Greek symbol. And torques cause changes in rotational motion, just like forces cause changes in rotational motion. The net torque is the sum of all torques acting on a body. So that's what we're going to practice doing today. So let's say that I have this square. The pivot point is the center of the square right here. So my pivot, I'm going to mark in green. So that's my pivot. And these forces are being applied. We have a 2 Newton force at each of these positions. And we want to determine the net torque acting on the square. So we would write a net torque equation. The sum of all the torques acting on the system is equal to, let's label these, and I'm going to color code them. So we have torque A, torque B, torque C, and torque D. Okay, so we have torque A plus torque B, that plus sign didn't turn out very well, plus torque C plus torque D. And these are all vectors, so the direction does matter. And you may notice that B is being applied, the force of B is being applied at the pivot. So any forces applied at the pivot are going to have 0 torque because R equals 0. So since R equals 0, our equation is torque is equal to R times F times sine theta. So if R is equal to 0, then our torque is going to be equal to 0. So we're going to write our net torque equation, and we're going to start with torque from A, which I'm going to do in purple. And here's radius A. And we can see that this is a 1 meter square. So if this is a 1 meter square, then this length of this triangle here is 1/2. This is 1/2. So this would be square root of 2 over 2. So for the radius of A, we're going to do square root of 2 over 2 meters multiplied by 2 newtons. And the angle between the radius vector, which is here, and the force vector is 45 degrees. So we'll do sine of 45 degrees. And this is negative because it would make it rotate clockwise. So there's some directions here. Clockwise is negative and counterclockwise is positive. That's just you can change it if you want, kind of like up is usually positive, right is usually positive, but you can change it if you want. But that's what it usually is. So since I'll just use the normal directions, so since that one's clockwise, it's going to be negative. Okay, then we have torque C, and torque C is going to make it go counterclockwise, so that's going to be adding. We're going to add that. And here is the radius C, which is the same length as radius A, so it's going to be square root of 2 over 2 meters times 2 newtons. And the angle between this radius vector and this force vector is 135. So we'll do the sine of 135, same as sine 45. So these are actually going to cancel each other out. And then we can do D, radius D here is the same length as radius A and radius C. So we have, oh, and D makes it go counterclockwise, so we're going to add it. So we have square root of 2 over 2 meters times 2 newtons. And then the angle between these two vectors is 45 degrees, so sine of 45 degrees. And we should find that the sum of the torques, I want it to be in black for the final answer here. The sum of the torques is equal to the sorry, that comes out to be 1, and we can see our unit is Newton meter, and it's going to be counterclockwise because it's positive. So that's how you would do that. Let's do one more example. This time, let's change the pivot. Let's change the pivot so that the pivot is now in this position in the bottom right-hand corner. And I'm going to label all of our forces. So we'll call this one A, we'll call this one B, we'll call this one C, and we'll call this one D. So the sum of all the torques is equal to torque from A plus torque from B plus torque from C plus torque from D. And we can see that D is acting at the pivot. So D is not going to exert any torque because R is equal to 0. So now we write out our equation. So sum of the torques equal to, so A is going to make it go clockwise. So we would have R, and this is R for A. Now that's 1 meter, so 1 meter times the force, which is 2 newtons, times sine of theta, and that's just 90 degrees. So that's just 1. I often leave it off if it's 90 degrees, but for showing you how to do this, I'll just leave it on there. Plus torque from B. Now B, oh, sorry, A was negative because it was clockwise. And then B is also clockwise, so we're going to subtract that one too. We're going to have a negative. The R for B here is this value. So that's RB, and that's going to be square root of 2 over 2 meters times the 2 newtons. And then we have D, or C next, excuse me. And C is going to be, this is RC, but what do you notice about the angle between these two vectors? It's 180 degrees, right? So let's see what happens. So this is RC. So we get 1 meter times 2 newtons times the sine. Oh my goodness, I forgot that. I'm so sorry. I forgot my sine on the last one. Sine of 40, or actually it's 135, sine of 135. Okay, so then this one, it's a sine of 180 degrees. And what's the sine of 180 degrees? 0. So this whole piece right here is 0. So if you have a force that is directed at the pivot point, you can't, it doesn't apply any torque. So then we could just calculate our net torque here, and I actually don't have that calculated right now, but I can do it real fast. Well, it doesn't really matter, but you can get your total torque right there. And that's all.